Thank you again, Marcelo, to organize this online version of the symposium. I have to admit, it feels a little bit weird to be talking about climate change in the middle of pandemic. It kind of feels like everybody has a more urgent problem to deal with. But climate change is still happening, still there. Global mean temperature is increasing. All climate models agree on that. But as you can see here, for example, they don't quite agree on its absolute value. So here there are different realizations of different climate models. And you can see that the global mean temperature can vary between 12 and 15 degrees. And if you think about it, that's quite a big difference. It's like 20–25%. And if you think that they solve the same system, that's, yeah, they're a little bit confusing. You would like a smaller difference. Well, they're not really simulating a quite easy system because the climate system includes a large variety of scales. It's a large variety of phenomena with very different both temporal and horizontal scales. And they all act non-linearly with each other. So an accurate climate model will need to resolve all of them. This is not quite possible at the moment, and climate models resolve only a tiny part of it, meaning the larger scales involved, so the so-called planetary and synoptic scales. One of the many reasons is purely numerical, because if you look at the equation of motion, the good old Navier-Stokes equation, you look at the momentum equation and you see already quite some term contributing to the CFL condition. If we want to translate how the CFL condition limit us in the type of scales that we can simulate in global models, you can see that if you want to include also the mesoscale and not just the global and synoptic scales, you will need to refine your grid of at least 2 orders of magnitude. Then you might Google a little bit more, and then you might find out that the smaller scales are also faster than the slow scales, which in turn translate in a ridiculously small time step that you will need to use to actually be sure to be converging to the correct solution. So you might be asking, okay, is it that bad if I resolve only a finite number of scales? Well, actually, yes. This is the case for two-dimensional turbulence. And here you can see that the entropy transfer from larger scale to smaller scales till it gets eventually dissipated at the very small scales, while energy backscatter from the smaller scale into the larger scales. Now, climate models have a truncation scale, which is way before the dissipation range. And this means that entropy cannot be dissipated where it should naturally dissipate and piles up at the truncation scale, making the model numerically unstable, while the energy of the unresolved scale cannot be backscattered into the large scales. This also implies that the total energy of the system actually depends on the location of the truncation scale, which is totally unphysical and totally artificial. Okay, so the idea of parameterization is that if we cannot resolve the fast small scales in a direct way, we can find a way to do it in an indirect way. And in particular, stochastic parameterization exploit this time scale difference between the slow resolved scale and the fast unresolved scale to model the latter with noise. This has been shown to have some advantages, like gaining computational time and reduction of model errors. But which exactly is the best parameterization for what? Still a matter of research. Many people are working on it. So for example, here, Memen and Holm derive stochastic formulation for the Navier-Stokes equation, either conserving the kinetic energy or the Kernel circulation theorem. Janssen and Held instead derive an extra term to be included into the equation to include the energy of the subgrid scale eddies. Kromening and Edeling use neural networks to represent the stochastic, the subgrid scale terms. I'm not going to talk about a new amazing outperforming stochastic parameterization, but I took the idea presented by Frank and Goldwald in their paper, and I look at how the model output is affected by my definition of the terms in the stochastic parameterization, and in particular, how the definition of the spatial covariance influence the model output. To do this, I use stochastic formulation for the two-layer quasi-geostrophic model. And to give you an idea of the complexity of this model, let's start from the shallow water equation. If you apply a scale analysis on them, then you're going to see that the rotational term and the pressure term are those highest in magnitude, and for a first level approximation, they balance each other. This is the so-called geostrophic balance, And as you might have guessed from the name, quasi-geostrophic approximation allows mode departure from the geostrophic balance, and the next term coming into play are the advection term and the time derivative. So as you can see, we are still quite far away from global circulation models, but nonetheless, it's still dynamically challenging, and it also can be representative of synoptic scale mid-latitude atmospheric dynamics, and also shows features like the jet similar to the real atmosphere. There are several formulations for the two-layer QG model. We use a non-dimensional formulation on a beta plane, which means that the Coriolis term is decomposed as a constant value plus some deviation in the meridional coordinate. For simplicity, I will show the derivation of the stochastic system when no external forcing or damping is applied, but we're going to see results also with external forcing or damping. It is formulated in terms of potential vorticity and stream function, potential vorticity represented by the letter Q, stream function, the Greek letter psi, and the two layers are the barotropic and baroclinic mode, represented by the pedix B and T respectively. So here on the right-hand side, you see the equation, the deterministic equation for motion that we start with. So here there's the evolution equation for the potential vorticity. These are the relation between potential vorticity and stream function. And here this equation for the total energy of the system. For our stochastic modeling assumption, we assume that the barotropic mode is slower with respect to the baroclinic mode. And we assume also that the noise acts directly on the fast baroclinic mode and only indirectly thanks to the coupling between barotropic and baroclinic mode also on the barotropic mode. How does this translate into equations? As I said, we use the idea that Frank and Goldwag presented, and their idea is to use an Oystein-Uhlenbeck process to represent the subgrid scale processes and include a correction term meant to guarantee the conservation of total energy. To do this, well, the idea is quite simple. If you have a manifold of constant energy, then you can decompose any vector in its tangent and normal component with respect to the manifold. And the normal component would be the one leading the dynamics to leave the manifold of constant energy. So the role of the correction is to cancel the normal component without changing the tangent component. To do this, we define a projector operator with respect to the manifold. And in particular, since the noise affects only the baroclinic mode, it's enough to project with respect of the manifold of constant baroclinic energy. So with this in mind, then we can apply Ito's formula and write the increment of the total energy. This can be written as some coefficient times dt, another coefficient times dw, where dw is the white noise. And overall, we want this to be 0. One way to have this equal to 0 is to impose both terms to be 0. This gives us a system with two equations, two unknowns, and we can solve for the correction term. So given this, we can substitute them back into our equations. And instead of having two separate stochastic processes, we have only one fancily written. Now, I haven't said anything so far, and also Frank and Gottwald don't say anything in their paper about how to define sigma and gamma, so the actual terms that are meant to represent the subgrid scale processes. I will show you that finding a proper definition for sigma, so for this noise covariance, is problematic enough. So for the forced and damped model, I will simplify a little bit my stochastic modeling assumption. So the equations are a little bit uglier because of the extra terms. Here there's the forcing, here's the bottom friction, the dissipation. And as I said, we simplified our stochastic modeling assumption. There is no gamma in here, and we just focus on the noise covariance. One way to define these terms is to use data. We have plenty of data, although we always complain we don't have enough, but we have quite so many. So we can use data analysis to determine them. One technique that is often used in climate science is empirical orthogonal function, also known as principal component analysis, proper orthogonal decomposition, choose your flavor. EOF looks at the direction that explains the largest portion of variance. So it comes as a technique comes from statistical analysis. Therefore, it needs long time series to actually give reliable patterns. So it needs indeed a lot of data. But on the other hand, once I compute the EOF patterns, I don't need to recompute them. I can use the same that I computed at the beginning of the simulation for the entire simulation afterwards. The other technique I will consider is comes from dynamical system theory instead, and it's dynamic mode decomposition, which relates to the Koopman operator. Now, if we have a dynamical system with an initial condition such that there is one unique solution, then we can define a flow map such that the solution at a later time t is just equal to the initial condition transported by the flow map for a certain time t. Now, any observable of the solution at a later time t can also be written in function of the flow map, and this in turn can be written as an operator applied to the observable computed at the initial condition. Now, this operator is the Koopman operator, and as you might already guess from here, the Koopman operator looks at the dynamics only for a certain time window, which you define. It means that I cannot really say that the Koopman modes have global in time validity, but they have only local in time validity, which means that I cannot just compute them at the beginning of the simulation and keep them constant during the rest of the simulation, but I should update them regularly during the simulation. This seems to be like a counterback, but on the other hand, I can choose the length of the time window that the Koopman operator is looking at. So the length of the time series I give an input to the DMD algorithm as a kind of a scale selection. So I can choose, I'm interested in this kind of scales, they evolve in this kind of amount of time. I look at these time windows and I focus on them, which is something that I cannot do with EOF on the other hand. Okay, this is all nice, but there is still one easier option, which is to assume that each grid point behaves like an independent, identical distributed random variable. And this simplifies my modeling assumption a lot, because in that case, I can only use a scalar times the identity matrix. I'm going to show you results when I consider the Inviscid scenario. Before that, just a few words about the numerical setup. We consider double periodic boundary condition on a 2 pi times 2 pi square. Use a grid point-based discretization. And whenever I refer to the simulation of the stochastic system or to low-resolution deterministic simulation, I refer to simulations that have been run on a grid with 128 square grid points. And whenever I talk about high resolution or reference solution, I refer to a simulation of the deterministic system run on a grid with 512 square grid points. Okay, so the parameterization is supposed to be energy conserving, so let's actually check that. And we can see here that there is a jump at the beginning of the stochastic simulation, likely because of the forcing, the system jumps to the next stable state, but afterwards it stays constant, seems to be maybe slightly dissipative in time, might be due to the Runge-Kutta stepping, which is known to have this kind of effect. But what is actually surprising is that if I compare it to the low resolution deterministic model, I see that in the case of the stochastic simulation, I have much lower amplitude anomalies. If I look at the field variables, that actually turns out to be a bad surprise, because this is the case for the baroclinic strength function, but the same holds for the baroclinic potential vorticity. You can immediately see that the pattern is completely different. It doesn't resemble at all the reference solution. And if you look closely also to the values in the color bars, you're going to see that the difference in colors are 2 orders of magnitude smaller than in case of the reference solution. And if I look at later times, this difference becomes even smaller. So the system is actually going towards, so the baroclinic mode is actually going towards a constantly spaced state, which is energy conserving, but boring to say the least. So, okay, maybe all that talking about EOF and might have been useful. Let's define sigma as a convex combination of the first 2 EOF. And again, I like my life easy when possible, and I put gamma equal to 0. So again, let's check the energy conservation. There is no jump in this case at the beginning, so the system stays on the manifold of constant energy defined by the initial condition. And the anomalies in the energy have actually amplitude similar or comparable to the low resolution deterministic model, which means that the energy conservation is not affected by the stochastic parameterization, but is mostly determined by the numerical discretization of the deterministic model. When I look at the baroclinic mode, this looks much better, looks much more similar to the reference solution. Also, the colors in the color bar are in the same order of magnitude as the reference solution, but you can still see they're not quite the same. So to have something more easy to quantify, let's give a look at the eddy length. And in case of the baroclinic mode, the stochastic parameterization doesn't really help, but it does in case of the barotropic mode, increasing the eddy length up to 9%. So that's something, that's an increase, but who said that I used the optimal structure for the noise? I could have used more EOF or maybe something else. To answer this question, we can see results of the first and damp system, where sigma is either defined as a linear combination of the first 5 EOF, weighted by the square root of their corresponding eigenvalues, or as a linear combination of the first 2 DMD modes, also in this case weighted by the corresponding eigenvalues. Before jumping to the result of the simulation, I want to actually check if EOF and DMD give me different results, or there are just two different ways to obtain exactly the same thing. And here you see the first and second EOF, and here is the real and complex part of the first DMD mode at the beginning of the simulation and at the end of the simulation. So you can see that EOF number 1 and number 2 compare pretty well with the first DMD mode. Although in case of the DMD, we can see that the eddy seems to be slightly smaller and they seem to have a less regular pattern. What is the biggest difference actually is given by the meridional location of the eddies, which is different in case of EOF and DMD, but also is different among the DMD itself at the different point of the simulation. So if you see here at the beginning, the eddies are around y equal 1, and later at the end of the simulation they are around y equal 2. So they actually moved towards higher meridional coordinate, and this is because of the forcing. The forcing that DMD cannot resolve directly with giving an eigenmode just for that, but EOF can do that, and therefore it does it by giving its own eigenvector for the forcing. Now, EOF 4 and 5 compare pretty well with the second DMD mode, although there are still differences. In particular here, there are some extra eddy structure in the EOF, which is not present in case of DMD. Okay, again, let's look at the energy conservation. The black continuous line is the reference solution. The black dash is the low resolution deterministic simulation. The blue continuous line is the ensemble mean, and the other color lines are just the different realization of the ensemble. So to cut it short, we could say that in both cases, the system is energy conserving. The energy anomalies are less than 2% over a quite long integration time. So according to the application, it might mean negligible. But since the purpose of this study is actually looking at the difference between the two techniques, we can see that in case of DMD, the ensemble members stay closer to each other. There's a reduced spread than with respect to the case of EOF, but the individual in the individual run seems to be more energy conserving. On the other hand, as I mentioned, in case of the EOF ensemble, there's a larger spread, but the individual simulation don't really always have the same behavior. Some simulation here seems to be slightly dissipative in time. Some others have a well-defined increasing trend, so they're not entirely coherent. Again, the differences are small anyway, so let's look at something else. And let's look at the difference in total variance with respect to the high resolution simulation. So again, when computing the L2 norm of this difference, we can see also here that in case of EOF, there's a larger spread, so the L2 norm falls into a larger interval with respect to DMD. But when comparing the values of the L2 norm with the difference between the low and high resolution deterministic simulations, we see that EOF doesn't bring a big increment, a big improvement, almost nothing, while DMD instead brings a more considerable improvement. Still not happy. Let's look at something else, and let's look at the eddy kinetic energy. So also in this case, we can see, as I said, the EOF ensemble has a larger spread in case of DMD, which also means that some simulations have very little eddy kinetic energy. Some others are even too many, even too much. But overall, they all have a tendency of mislocating this double peak behavior by placing it towards too high meridional coordinates. In case of DMD, instead, the ensemble members stay closer to each other. They stay quite close also to the reference solution, and they do a much better job in locating the right position of this double peak. So to wrap up, we saw the effect of different definition of the spatial covariance in the stochastic parameterization for a two-layer quasi-geostrophic model. In particularly, I showed the cases when either no structure is defined, so it's just assumed that it's independent, identically distributed noise, or when it's defined by means of either of empirical orthogonal function or dynamic mode decomposition. The results showed us that mathematically correct is not enough. We have to take care of the dynamics or the physics that the system is modeling. And also we saw that using a constant in time pattern leads to a larger spread into the ensemble, but not always to the best improvement into the results. While on the other hand, dynamic adaptive definition of the spatial covariance leads to a smaller spread into an ensemble, but had greater improvement in the total variance and in the eddy kinetic energy. So I'm pretty sure we can all come up with a long list of questions, all starting with what happens if, for example, what happens if you consider other parameterization or a more complex model. Here are just some examples. I'm pretty sure we can all come up with a much longer list. Or maybe you already have some of this, the answer to some of these questions. In this case, please contact me. I will be really happy to get to know a bit more about it. Or also, if you're just interested in working to find the answer to some of these questions, again, please contact me. I will be more than happy to receive your email. Thanks.
Okay, thank you very much for the nice talk. Are there questions from our small audience here?
Yeah, I think I'd have a few questions. So you mentioned Darrell stochastic, as in Darrell-Holmes stochastic setup, which is more towards the Kelvin circulation theorem. Mm-hmm. I think I've been working quite a bit on the quasi-geostrophic stochastic theory recently, Darrell's group. Do you have any opinion on which approach is sort of better in which scenario, the energy conserving setup or the Kelvin circulation theorem conserving setup?
So that's an interesting question. That's also, and thank you very much. That's also difficult to answer because the approach of Darrell is completely different because he's basically changing the equation of motion. He's not starting from a deterministic equation of motion and adding a stochastic forcing, but is really including the stochasticity inside the equation such that the physical properties are still ensured. I think I already also talked with one of, not Colin Cotter, but Igor, another one of their crew, I don't remember the name. And I think they're using EOF to define this kind of structure because, yeah, as I said, it's easy. Mm-hmm. The problem with DMD is that you actually have to see generally how it can be incorporated inside the model. So, like right now, I was running the simulation just in sequential mode, so I didn't use any parallel techniques. But already here, the problem is to see also the scalability of DMD in parallel and how easily it can be included into the model, because this thing of having to update it regularly can be a drawback according to the model implementation. So you really have to go and look at the numerics that is done in the model itself.
I see. So I guess that depends on how the discretization is parallelized and how easy it is to.
Yeah, I think a lot will depend also on the numeric itself and how easy it's to fix one such that you can incorporate one technique instead of the other.
Yeah. That's really interesting. I really wonder how the two quasi-geostrophic setups compare.
Yeah, I didn't compare the two, but yeah, it would be interesting.
I think I've only started working on this in the last 2 or 3 months or so I don't think I have any results themselves yet. But that would be interesting. Yeah. And then another question I had was, so I guess the Hummelkutta time discretization is fairly good in keeping the energy conserved. You said you used some kind of Arakawa grid for the space discretization. Is that energy conserving, the space discretization?
So the Arakawa scheme is energy conserving and entropy conserving per each truncation scale. So on the as far as it regards only energy conservation, that's fine. But that also means that it might make the physics a little bit less realistic. So for a purely numerical point of view, energy conservation is fine. From a physical point of view, you might want to consider another scheme instead of the Arakawa scheme.
Okay, I see. I guess you could include some kind of entropy dissipation methods and still keep the energy conserved or something like that.
Yeah, there's plenty of things that could be done. Yeah.
Okay, that's interesting. Thank you. And then one last question was, how do you choose the refinement level? So you said the coarse one was 128 and the fine one was 512. Mm-hmm. Is there a particular reason why you use this particular refinement level, or?
And computational time, I guess, mostly. Like I wanted something that the stochastic model could run relatively fast, so I could run more simulation and see how it was doing. But still, of course, not resolving all the scales, and also not having two cores, because then I guess the difference between the separation between the resolved scales and the unresolved scales that you're trying to parameterize might be too big, and then the numerics might not be able to deal with that.
Okay, that's interesting. Thanks.
So if you look at the difference in your total energy diagnostics between the reference simulation and the deterministic low resolution simulation, then it didn't actually look very sort of drastic, that change. And the different realizations of the stochastic parameterization seem to be far exceeding the range between reference and low resolution deterministic. Is that really what you want? Could you comment on that?
I have to say that a posteriori, I'm not entirely happy with the parameterization I chose, because this idea of constraining on the manifold, I'm a bit afraid that doesn't allow to actually reinject the energy of the subgrid scales, because you're pushing it down. So I'm not entirely sure how well the parameterization is doing on that regard. That's also why I didn't really focus too much on the parameterization itself, but I decided more to focus on how I should build the parameterization, so how I should define, like, the different ways to define the spatial covariance. I'm pretty sure that, there are probably some parameterization that might perform better, and therefore the energy analysis might be more insightful in that case.
But if you ran for a longer time, so this is probably a relatively short amount of time as compared to the eddy turnover time, or is it already a long time around that you're performing here? Would you expect that for the low resolution deterministic simulation, you actually lose much more energy than you would like to lose? Is that the situation that you are in?
In this case, so it's already quite a long simulation, because like 5,000 time units in this setup is something like 34 years, and the eddy turnover time is around, if I remember right, 12 time units. So
okay,
it's still
long.
It's long.
Yeah.
But again, in this case, I don't really know what to expect in energy term from. I don't really think that the low resolution would lose a lot of energy, because it's already long enough that in case it would have lost it already.
Okay.
So I'm really not entirely satisfied with the parameterization itself. But yeah.